So, welcome back to the lectures on GPU architectures and programming. So, in the last weeks we have been discussing more on memory access and coalescing related issues, and throughout the last few lectures while studying about warps and their scheduling, the divergence and how memory access is coalesced, we have fundamentally understood the GPU architecture's memory hierarchy and how it can be used to write optimized programs. So, with this background we are going to this topic of optimizing reduction kernels. That means we will try to use these concepts for some regular programming jobs, the primary one being a reduction kernel. So, these are the concepts which we have already covered, and we will be trying to use those concepts here. Now, before getting into reduction kernels, we have to understand that in general, while doing parallel programming, what is important is to understand the concept of parallel patterns. Now, a parallel pattern would mean a specific pattern of tasks, that is a specific execution order and data access order of tasks which can be found occurring very frequently in some algorithm. So, if I have a specific sequence of computation and a specific sequence of data access that is occurring very frequently, that is what we call as a pattern. If that has lot of parallel jobs embedded in the pattern in terms of computation or communication of data, it's a parallel pattern, and we can see such parallel patterns occurring in very large number of computation intensive things that we do. For example, matrix multiplication, for example, convolution, and also the reduction operations. So, we will try and focus first on reduction operations. Now, typically what is a reduction operation? So, a reduction algorithm or reduction operation is primarily the name of it's a generic name for any operation that takes as input a vector and reduces it to a single value via some associative operation. For example, sum, mean, max, as you can see that these are all associative operations. So, like suppose I am computing the mean, it's same as if I write right. So, this is a generic name for operations which reduce a vector to a single value, and for fundamentally the operation has to be an associative operation, and these are operations which may visit large number of elements in the array. I mean, so you have lot of elements and you carry on this associative operation to get to the final value, and fundamentally you will need to visit every element in the array and perform the operation. Now, since and this is interesting from the point of view when I have a very large array to work with. So, a very large vector, lot of values, and my final goal is to reduce it to a single value. Now, why is this interesting? Because this is kind of a pathological workload. So, in this case, as we can see that there is not much of compute operations to do, but significant amount of memory operations to do, and since there is lot of memory operations involved, we feel that most of the optimizations we have discussed earlier should have a role to play in case of reduction algorithms, and that is what makes them interesting in this context. So, we just start with a parallel sum implementation, right. So, you have a lot of numbers and you want to sum them. If you have a sequential version, it is going to be an order of n operation. If you are going to do a parallel version, which we have seen earlier in some other examples earlier, it is going to be a log n operation, right, because you have threads which are working on different parts of a large array. The array is n sized, and you are going to do the sum, and then you are going to compute the sum of sums, so on and so forth. So, it is going to be a log n operation. Now, if I am going to do a large this kind of a parallel reduction on a large array, then first thing is I will require multiple thread blocks, right, because one block can only accommodate 1024 threads. I need more than that, so definitely multiple thread blocks. Now each block can reduce a portion of the array. Now once that has been done, I need the results to be communicated, right? Because each block may reduce a portion of the array, and these portions will need to be reduced further, but that would definitely need global synchronization across blocks. Now we know that using sync thread kind of mechanism, we can only synchronize inside blocks, and CUDA doesn't support global synchronization. So essentially you have to design a reduction kernel for a block, and you have to call it multiple times and use the results of each block to do the computation over the results in a significant number of iterations. So what for our purpose here, we need to understand that this is just a small picture we are trying to show, that if you have a very large size data, it needs to be decomposed into subparts. So you decompose the computation of the overall sum across multiple kernel invocations, and the kernel launch serves as a global synchronization point. That so after every kernel launch, when you get the data back, those are the synchronization points from which you can gather the data and again launch further kernels, right? So this is kind of a sequence tree of kernel launches which we are trying to show, that you have large data, with each launch you get some part reduced, and finally it comes down to one block. So here we have examples of codes of how to do this reduction, but we will actually use them more for the assignment purpose, and for our discussions we will focus more on a single block reduction and how that can be accelerated. So before getting into that, let us understand what are the metrics for GPU performance which we will use. Of course, this is something that we have seen earlier also. This is just a mere recap. So ideally we like to achieve more number of gigaflops per second. Flops is floating point operations per second, right? More number of gigaflops, and so in term this is basically about the compute that total I can do for compute bound kernels, but in this case it's more of a memory bound kernel. So I would like to see that I am being able to use the full bandwidth of the memory, that is the full rate at which data can be read or written into the memory subsystem, whether I am being able to use that. Now in this case, if I am just doing a small reduction operation, it has low arithmetic intensity, as we have seen earlier also, right? So it's more like we are going to optimize for achieving the highest possible memory bandwidth that I can get here. So the first possible technique here for reducing a block here would be to use interleaved addressing. Now this is some algorithm which you have studied earlier also. This is just a brief recap. So what we do is we have this many data points to add, and what we are doing is we have launched half the number of threads, right? I mean essentially there are threads but we are not utilizing those threads here. But there must have been threads which have, all the threads have copied the data to the shared memory. By the way, I will just repeat, this is the optimization when we are talking about it. We are doing it in the shared memory, assuming that threads have done a per thread data load into the shared memory, right? So this is the first job. Each thread loads one element from global memory to shared memory, and then I will actually engage half of the threads to perform the first level of addition. A thread adds 2 elements, and half of the threads are actually deactivated after the initial load because they don't have anything to do, because one thread can add 2 elements. So all the threads together collaboratively load data, then half of the threads perform the step 1 of addition. This addition is performed in a stride of 1 because you use the thread IDs corresponding memory indexed value and the next value, right? And then in the next iteration you just increase the stride. So the thread ID, the thread will add the location, its own location's value plus the data sitting at a stride of 2, and then stride of 4, and then stride of 8. In that way finally the 0th thread will compute the final sum, right? So this is the reduction kernel. Again I will repeat, we have seen it earlier, but here we have to repeat it because we need to understand the starting point and what are its flaws, right. So, first thing you do is you load the data into the shared memory, right. So, this is the load operation, and then once that is done, after a sync thread, when all the loads are done, you start doing the reduction. So, this is the reduction loop. You start with a stride of 1, and in each iteration of the loop, you reduce by 1 level. So, stride of 1, you do the first level reduction. The second level, you operate with a stride of 2. So, essentially you operate on consecutive data points, that is stride of 1. You operate on 2 stride valued data points, so that is stride of 2. So, that is what we have here. So, s equal to 1, you do 1 level, then you multiply by 2, you go to stride of 2, and then you again do the addition for if on this values that are loaded in the S data shared memory array, and they are indexed by the TID, right. So, each thread does the addition at a stride of 2, then in the next iteration at a stride of 4, because you again multiply by 2. Now, what are the good things and the bad things here? Well, you have parallelism, you have the threads loading the data in parallel, and then you have the threads doing the addition in parallel, although half of the threads are not used. The bad thing is the modular arithmetic done here is very slow. So, for every thread you are doing a thread ID percentile 2s, right. So, you have to identify that whether this thread is the one which is supposed to do the job of addition, or whether this thread is going to sit idle. Because as you can see, with every level, half of the threads further go idle. Whatever were the active threads in the earlier iteration, half of them would go inactive, right. So, in every iteration you take the TID and do a percentile 2s to find out whether the TID will remain active or not. If it is active, then you do an addition with a stride of value s, right, and you keep on doing this until and unless your s is up to the half of the block dimension. That means you have reached the and you have actually summed up all the values, and you are only at the last level. And then at the last level, you have the value available in S data 0, which is the final sum, and that is what is returned back into the global memory. So, this was our reduction kernel. For this kernel, you can write a host program, and of course, it will be quite complicated in case you are going to launch it again and again for reducing in different parts of the memory. So, this is the host code which we are not discussing right now. We will actually provide some nice assignments using them, and those will be useful, and it will be described at that level. But try and understand the kernel's execution here. So, this is the reduction kernel, right, and as you can see, first problem is it is highly divergent. Why? Because inside the loop you have this percentile operation which the thread may or may not satisfy, and the modular arithmetic which is computing this is very slow. Warps are very inefficient due to the reason that in every warp you have divergence, and anyway half of the threads do nothing after performing the global load, and also the loop is expensive. So, some statistics here, considering an array of this size, if we perform this, if we actually execute this reduction kernel multiple times using multiple kernel launches using a GPU that is the K40, this is the bandwidth and execution time that we can see here, right. So, just repeat that this is not an execution of one kernel launch. We are actually following this picture of orchestrating multiple kernel launches and finally getting the value. Well, inside each kernel launch, the code we execute is this one. In each launch, you actually reduce some part of the array. So, as we understand that there are significant number of problems in this reduction code. First of all, it is highly divergent and warps are inefficient. The percent operation also is very slow, and we like to replace it. So, what can be the next possibility? The next possibility is that you do interleaved addressing. That means you replace the first thing is I will like to remove the divergent branch from the inner loop, right, and also I will like to remove this divergence, but still of course I will use strider index that will help me to remove this percentile operation, and also the situation that in every execution of the warp, consecutive thread half of the thread IDs actually diverge, right? Now how can we do that? If we look back into the picture here, let's understand the divergence here. So in the first iteration itself we can see the divergence because these all started inside a single warp. Now inside a single warp at this point, due to that percentile 2s TID percentile 2s operation, the divergence came in because only these threads progressed, right? So essentially inside the warp you are getting half of the work done, right? Now this doesn't look very bad here, but consider large number of warps working for a big block of code, right, for a big thread block. So that would mean inside each warp you have half of the threads not doing the addition at this level, and again half of the threads not doing anything here. Try and understand there is a difference between the situation that you have half of the threads going inactive and half of the threads inside a warp going inactive. So again I will just repeat, there is a difference between half of the threads going inactive. Well, that's the property of the operation here. But if half of the threads inside a warp go inactive, then your warps are not efficient. Whatever operation the other threads are supposed to do, they are not synchronized inside a warp. Alternative would have been that whichever were the active threads, whichever were the threads that are supposed to do the real addition, if I can pack them inside the same warp, that would be more efficient, because as you can see here inside the warp half of them are progressing. The reason is the thread IDs are what, 0, 2, 4, 6 like that. Had the thread IDs of this thread itself been 0, 1, 2, 3 like that, then looking into a warp of size 32, I could have said that okay, all the threads are working. So originally there would have been a higher number of threads which have done the load, but then inside the warp every thread is working. So try and understand the difference. Half of the threads getting inactive at each level is one thing, but still if the threads which are working are having consecutive ID, that would mean that they are packed inside the same warp, and when the warps execute I have fast progress, right? Now that's what we achieve with this reduction 2 here. So we will do some modification in the code to ensure that although half of the threads go inactive, but the threads which are really working are of consecutive ID. That would ensure they are executing inside a warp and they are all progressing in parallel, because if you extend this picture you have 32 threads which are inside a warp. That would mean in one lockstep this step of the reduction would get done, which will not be the case if you extend this picture for the earlier reduction 1 kernel. Try and understand this. Now, so with the difference, as you can see between these two pictures, is with respect to the thread IDs, that which thread is doing the job. So here I still have half number of total threads doing the job at each level, but the threads are all sequential in index, they form a common warp. I have removed the divergence, so whoever has the job to do, they will be doing the job maximally. There is no idle slot, there is not the case that a warp is divergent and some of the threads are not working, at least in the initial parts of the reduction. Now that would significantly speed up the execution of the code when I launch the kernel multiple times and reduce in different parts of the program. So how to do this? So essentially what I want is still my stride is going to increase from 1 to 4 like that, but the thread ID is going to be like this, right? So while doing the reduction in the shared memory, this is just a snapshot of the reduction 1 kernel. These were the problems. The first problem was this TID percentile operation, and that was slow and that was also creating the divergence. But now we do a different thing. So I have a more complex access expression. Earlier my access expression was identity map, right? So every TID will map its corresponding index data in SData. But now what I do is, for every TID I multiply it with S and 2 to get the index where it is supposed to work. So initially S is 1, that means If the TID is 0, it's working on the 0th location. If the TID is 1, it's working on the 2nd location. If the TID is 2, it's working on the 4th location, so on and so forth. So that's what we want here, right? TID 1, thread, these are the thread IDs, it's working on location 2. TID 2 working on location 4, TID 3 working on location 6, like that. And that is achieved by this modified access expression. And how long will this work? As long as the index is less than the block dimension. And of course, the stride remains the same. So the striding mechanism remains the same from 1 to multiplied by 2. That's the hop. In every hop you multiply by 2, you start from is equal to 1. But you change the access expression from a simple identity map to 2s multiplied by TID, and that gives you this nice access pattern of threads. So with this modification, you have warps getting utilized, lack of divergence. So you remove the divergence of the threads, and you remove the complex percentile 2 operation, but this also will suffer from the shared memory bank conflict issue, which we will see soon. First, let us understand why we will have the shared memory bank conflict. So as we can see that we will have a shared memory bank conflict here. Now, if we look into this picture, so every thread is accessing 2 consecutive locations, right? The next thread is again accessing 2 consecutive locations, so on and so forth, right? So with this, if you look at the way the threads access the shared memory, so thread 0 access bank 0, bank 1, thread 1 access bank 1, bank 2, like this. So if I draw the picture for a collection of threads, I would see that I will have inside a warp, I will have 2 threads accessing the same bank in parallel, right? Since every thread accesses parallel banks, the number of threads in a warp is equal to the number of banks. So I have a two-way conflict for every thread. The accesses are not uniform across banks. Every thread is accessing 2 consecutive banks. So I have a bank conflict here, right? So if more than one thread attempts to access the same bank, we know we get the bank conflict, and that needs to be resolved now. And the way that you can resolve it is you have to again perform some transformation into the code. Now, again we will try to see that so every thread these accesses it's doing, they are accessing into consecutive banks, right? So how can this be modified? It can be modified by doing a sequential addressing. So you don't go from stride value equal to 1 and keep on increasing the stride, but rather than that you keep on decreasing the stride. Now how does this help? Because then when the threads are going to perform the loads will not have loads from the shared memory, you will be able to remove the conflicts. So this is again something I think before getting into this you should go back and read once the literature that we studied about shared memory. So at this point we will be stopping today's lecture, and we will resume in the next lecture from this reduction 3. And so just to summarize, in the 2 reductions that we have discussed, the first was the original reduction where let me just go through the picture. We had half of the threads working, but the way the thread IDs are being arranged, inside every warp I have half of the threads working. That was a bad thing. In order to remove that, what we did was we came up with nice and intelligent access expressions, so that if inside every warp I have all the consecutive thread IDs working. That gave me some speed up. But as we can see, if I do a memory access analysis, there is an issue of bank conflict here, and we need to remove that. We will see how that can be removed by doing further modifications to the expressions in the program. And with this we would like to end our lecture here. Thank you.